Mehdi of C3AI. So this is a meetup, the San Francisco Bay Area ACM. Welcome to our tonight's meetup talk. So introduction, San Francisco Bay Area ACM was founded in 1957. So we were a meetup long before meetups were a thing. We're a nonprofit focused on promoting knowledge of modern computing. We like to create community, support networking and hiring. We have only a $20 annual membership. We have 2 monthly meetings, a general computing meeting, usually the 3rd Wednesday of the month, and a data science SIG or special interest group, typically the 4th Monday of the month. When we were in person, we were also doing networking and job announcements. I think we should work on that for our virtual version. We also have a joint meeting schedule with other IEEE societies and ValleyML.ai. If you'd like to become a member, there's a $20 annual membership. You can sign up at sfbayacm.org and click on join. Some upcoming webinar events we have. On Saturday, June 27th and 28th, there's Deep Learning for Natural Language Processing with PyTorch, AI workshop on machine translation. Instructors Ravi Alongo, a senior data scientist at a stealth startup, and he's helped teach a number of our workshops in the past quite successfully. I've worked with him and he's been a very good instructor, a very well organized technical person. Tuesday on July 14th to September 10th, there's a machine learning and deep learning boot camp by ValleyML.ai. So that's a series of talks. On Monday, July 27th, there's knowledge graph extraction from unstructured data and semantic role labeling. So Ravi will also be giving that presentation. So if you'd like to have any questions, use the Q&A in Zoom for questions to the speaker. You can also use chat and YouTube for questions or for tech support. If you want to give announcements for jobs or other events, post on the meetup comments. So for an introduction, Dr. Maasoumy has a PhD from UC Berkeley in 2013. He specialized in optimal control and machine learning. He leads AI teams to develop ML, deep learning, and optimization algorithms to solve business problems with staggering value across many industries, such as energy, manufacturing, banking, and finance. Dr. Maasoumy has authored more than 50 conference and journal papers and book chapters. He's won several academic awards. Some are among 3 best paper awards. Mr. Shouvik Mehdi has studied statistics and machine learning at Carnegie Mellon University. He currently focuses on many new ways to incorporate domain knowledge into ML models and to improve performance in high-dimensional, small data settings. He's worked with predictive maintenance and engineering diagram digitization, defense, and oil and gas industries. So I'd like to turn it over to our 2 speakers. I'm going to stop sharing now. Mehdi, go ahead.
Right. Thank you very much. Hello, everyone. Thanks to the organizers for having us. I believe my slides should be up now. Is that right?
Yes.
Okay,
yes.
Cool. So enterprise AI. Shouvik and I will be talking about what might be one of the most untapped opportunities for impactful work in AI today. We all have seen applications of ML and AI in our daily lives, ranging from movie recommendations to self-driving cars. But the question is, how can AI help companies and large enterprises in solving their previously unsolvable problems? And how can it bring economic value by doing so? Especially to more traditional type of companies in areas other than tech, where, say, energy, finance, or manufacturing verticals who are sitting on piles and piles of data, but may not have the right tools, the right expertise, or even the right DNA to leverage this data, and in order to make better business decisions. So today we will be talking about those companies and how we are helping them go through this journey. We will argue how the confluence of four technologies is driving digital transformation and is fundamentally changing the way business and government will operate in the 21st century. These technologies include elastic cloud compute, which essentially provides unlimited and affordable computation and data storage. It includes big data, which enables analysis of whole data sets with no needs to sampling and essentially no sampling error. It includes Internet of Things, which makes everyday devices essentially a computer, creating a computing platform of unprecedented scale and putting them in our pockets and on our wrists. And last but not least, AI and machine learning, which powers prediction engines that can rapidly and accurately perform specific tasks having learned from data. At C3, we leverage digital transformation enabled by these technology vectors to solve previously unsolvable business problems. Digital transformation is making an impact on virtually any industry that has or is sitting on lots of data, from manufacturing to utilities to healthcare in the form of applications such as inventory optimization for manufacturing processes, anti-money laundering for banking, and predictive maintenance in quite a few industries. For the rest of the talk, we will be focusing on one of these applications, namely predictive maintenance. And we will walk through a typical AI-based predictive maintenance projects, highlighting how it's different from a traditional software engineering project. We will talk about use case selection criteria. We'll talk about data availability and data quality and their implications on decisions that will have to be made across the course of the project, and other business requirements of these type of projects, such as interpretability of AI models and implications of those decisions that let's say, data scientist or an AI researcher would have to make before or during the course of the project. We'll talk about open research problems later on, that essentially either us or the AI community are working on these days. And we'll dive into two use cases, namely automatic digitization of engineering diagrams using deep learning and graph search, as well as a new algorithm that leverages distant metric learning to provide a regularization framework that leverages expert knowledge in the learning problem. These are some of the works that came out of recent projects that we've been doing, and we've been publishing them recently, and we'll be talking through those sets of work. Let's start from what predictive maintenance is and how AI is useful there. You may remember back in July 2019, which is less than a year ago, but now seems like eternity, thanks to the pandemic we're living through, that there was a widespread outage in New York City that essentially sent the whole or chunks of of Manhattan into outage and into darkness, and it caused a lot of chaos in the city. More than 70,000 people were left in the dark with no power outage, stuck in elevators or stuck in the underground, and it did in fact put a lot of lives in danger. This is only one of these examples of cases where a critical asset, which is highly instrumented, it's collecting a lot of data, fails without any warning, right? Without any way to detect that warning or predict it. And you might wonder, could we have used all this data that is being collected to predict or even avoid such failures, right? And examples of why there's other examples on other type of predictive maintenance projects that we have worked on across different industries. that include predictive maintenance on renewable assets, such as wind turbines, aircrafts, mining trucks, pharmaceutical machines, which might be working nonstop on producing, let's say, 14 billion doses of vaccine, and you want them to be working all the time and not stop working. So let's look at the maintenance problem, how it's been done historically in order to avoid these machines from failing. The maintenance paradigm falls into two categories. One is a reactive maintenance, and the other one is proactive. Reactive maintenance has to do with the type of maintenance where you essentially sit around and let the asset fail, and once it fails, you jump on and start replacing or repairing the asset. So you pretty much don't do anything. But on the other hand, the proactive maintenance has to do with the techniques where you use in order to prevent or predict a failure and avoid, potentially avoid those failures, right? Avoid repairing or the whole failure as a whole. On the reactive side of things, when you, if you look at the way this is done, the idea is essentially run to failure. So you essentially let the asset or the machine run. There is not much you do in the meantime, no preparation effort, but on the disadvantage would be a high downtime, high repair, and high overtime labor cost. On the proactive side of things, we have the preventative maintenance, where the idea is to use recommendations from instructions or from user manuals that typically come from the manufacturers of the asset in order to perform certain actions, in order to increase the asset lifetime and reduce the unplanned downtime. But the disadvantages are that you don't actually consider the true wear and tear of the asset, which leads to excessive maintenance cost. You tend to do maintenance when it's not necessary, or you will do maintenance too late after the asset fails. But the subject of this talk is on predictive maintenance, where we can use data, when we can use machine learning and AI models in order to come up with a cost-effective way to predict these failures accurately, predict when the failure happens, increase the asset life cycle, and minimize the downtime. And on the other hand, what this paradigm requires companies and people is that you would have to scale up the staff. You need to make sure that the staff that is using the solution knows how to interpret the results of an AI model. And you essentially have to be very careful about change management that has to happen across the organization. Okay, let's look at basically predictive maintenance and how AI can help us. AI, thanks to the AI-driven predictive maintenance, the problem is now much more scalable and less labor-intensive compared to the physics-based approach that this problem used to be solved with, kind of first principle type of models, which was very labor-intensive. We can surpass the performance of SMEs or the domain expert, which typically have been working with these machines for decades, within a few months of work, leveraging the data and leveraging the historical failure examples, which leads to significant socioeconomic value for the industry and the society. And that's what we call superhuman performance. You can surpass human performance in a very short period of time. And the other benefit is that you preserve institutional expertise before the experienced senior human and subject matter experts leave the organization. As you build these features into the machine learning model, these are coded and codified and are preserved in the form of input features and eventually as part of the model itself. And they will be persisted there even after the human who gave the idea to those features might leave the organization. And thanks to the power of deep learning, We are no longer dependent on subject matter expertise when it comes to feature engineering, as given enough data, given lots and lots of data, we don't need actually that much of subject matter expertise input. Okay, now let's consider 3 different scenarios. I want to put in contrast 3 different scenarios. One that we have no detection capability, the one that we have anomaly detection capability, and one with predictive maintenance capability, and see what's the tangible economic value that these algorithms bring to the table. In the case of no detection capability, as you can see, the green is operational time, and orange, red, and gray are essentially non-operational times when the asset fails. In this case, you have no foresight of the failure, so you will be surprised by it, and you will have to schedule work orders, leading to months and months of downtime. While if you have an anomaly detection capability, you can essentially, as soon as the onset of failure starts, you can detect that, and you can start and kick off the work order, start collecting the parts, bring the parts that need to be replaced, and shorten that offline period by quite a bit. And the best of all is when you have a predictive maintenance capability, which means you can leverage the data, historical data, and you can foresee when a potential probable upcoming failure is about to happen. And you can even look at the evidence package, see what type of failure it's going to be, what part of the asset might be failing, and start preparing for that. That can lead to increased operational time and significantly less downtime, resulting to economic value for the organization.
A question. What are your strategies to choose between the anomaly detection approach or a predictive maintenance approach?
Very good question. I actually have quite a few slides going to the details of those and why and when you want to choose one over the other. I don't keep you waiting for so long. We'll get to that soon. All righty. So this is a typical AI-based predictive maintenance project. Essentially, we will talk, I'll walk you through this process, which is pretty short. We typically do these projects in between 8 to 12 months, weeks, not months. It's 8 to 12 weeks, very short period of time. And the type of I'll talk about the type of considerations and the decisions that we have to make, both pre-project kickoff and during the course of the project. Before the project starts, it's a period which is as important, if not more, than what you do during the course of the projects. Before the project starts, we're dealing with several challenges, including use case selection, and including some other challenges that I will talk about. But let's start from use case selection. When, let's say, you are introducing AI to an organization which is quite foreign to the idea, and you want to see what use case should I start from? If I have an array of use cases that I can pick from, what is the one I want to start with? A few years ago, Andrew Ng, who anyone that has anything to do with machine learning knows, had a very interesting tweet. He mentioned that pretty much anything that a normal person can do in less than 1 second, we can now automate with AI. So that's a profound statement. It talks about the type of use cases, the type of project that we'll have to pick for our AI use case. However, that turned out to be false, as Pedro Domingo, one of the other big figures in the space, commented that a human can actually do all sort of things in less than 1 second that the machine and AI cannot do yet. However, that's besides the point I'm trying to make here. The point here is that the mere existence and sending this tweet by itself, the mere point of that is that it conveys an importance of what kind of problems and projects you should focus on. And you should essentially have your AI model to automate. You should start from easy tasks, not the hard ones. And that's indeed one of the guidelines that we have in mind as we enroll AI into new organization as our first use cases. So that's one of the first ones, first challenges, use case selection. Let me walk you through an example. Let's say you have, you're a data scientist, your boss comes to you and it says, I have two ideas for a first use case. Tell me which one is the best. The first one is as follows. You have an expensive machine that the operators of the machine, even looking back retrospectively, they cannot figure out when it would break. And you would have very few historical data points and failure labels to learn from. So you want to use AI to detect that, to learn from that. To us, that's not a good idea for a first AI use case. While on the other hand, a good AI use case would be one that basically you have many machines where a human operator can easily see that it's about to break, but you can't possibly check them all. You have, let's say, hundreds or thousands of these machines, and hence you have hundreds and thousands of historical data, so a rich data set relatively that you can learn from, and the machines are heavily instrumented. So this is the contrast between a good and a bad first AI use case. It kind of gives you an idea where to start from. What are the other questions that we ask when it comes to use case selection? Data quantity. Data quantity is one of the most important aspects. Unfortunately, in a lot of industries, we have a lack of data. You might have heard about big data, but believe it or not, small data is the real problem, where a lot of companies and a lot of processes have to be automated while there's not much data. So later on in the course of this talk, Shouvik will talk about how we derive this new algorithm that allows essentially subject matter expert knowledge to be embedded in the learning problem using a distance metric learning regularization. Data quality is another aspect which is very important when it comes to being able to get a good results from machine learning models. Labels will determine whether you will use a supervised or unsupervised approach. Oftentimes you have labels, but there's also a lot of cases where you simply do not have any positive cases or any labels. Sometimes it's worth delaying project and spending some time on collecting data, but it's not always possible. Let's say you have a nuclear reactor you want to apply predictive maintenance to. You cannot possibly create some fake data, let the reactor fail and see what happens, and we can learn from that. That's not possible. So you have to live with lack of data and lack of labels in a lot of use cases. The other considerations include deep learning. Do you want to use deep learning or not? There is a trade-off there too, where deep learning models are typically a lot more higher capacity. They can estimate a lot more complex models and relationships, but they come at a cost of lack of visibility and lack of interpretability. You want to make sure that there's a current baseline established and the performance required for adoption of the solution is established before you start working on the project. You may want to also establish a value calculation formula where you essentially link the performance of your algorithm to a monetary value or to some sort of value to the organization. And last but not least, you may want to be careful about whether there's a need for evidence package. There's a need for basically showing what is contributing to a high probability of failure or high risk score and what's not. And these are all these considerations that you want to take into account and think about even before the project starts. So I'll walk you through one real example. This is a note that comes out of a use case scoping workshop. You hold a workshop with customer. And what customer wants is a predictive maintenance application where you can use historical data to predict failures or detect anomalies. And the project manager comes to you as a data scientist, and he's very excited. He says, we have a new project, get excited. We have a customer that wants to do predictive maintenance on, let's say, compressors or turbines or whatever. We have 50 of those assets, very large and very expensive assets. And we have the available data include 10 years of process data, let's say sensor readings, 10 years of maintenance data, and 30 shutdown events per year, which are related to reliability issues. Okay, that's all you get. That's all you get from the project manager, as vague as that. Now, as a data scientist or AI researcher in the organization, you have to start thinking and asking some sort of certain questions. You need to be asking, do we have the same set of sensors across all these assets? Or each asset has a different subset of sensors? That may dictate whether you can use one model across all assets or not. You may want to ask about, do you have full data coverage for all the sensors across these 10 years of data? Or are there gaps in the data? Are there sensors that have been recently installed? Are all these failure or shutdown events unplanned, or some of them are planned? Are they all predictable? Are they all valuable to predict? Because every data point has a history behind it, has a story. Every failure or shutdown has a story behind it that could be, a planned shutdown that may not be a value in learning from that, or it might be misleading to your model if you take that as a positive case and try to learn from that. So these are all interesting questions and considerations that you have to take into account. Are there any sensors that you may have recently installed? That means you won't have any, or you will have limited history for those sensors. Are there at least 6 months of sensor data before every failure? So let's say if they tell you there are 30 shutdown events, if half of them were so far back in the past where you didn't have sensor data, those are essentially useless. These are the type of second-degree questions you want to ask. Do we see significantly different operation regimes across time and assets? And is the goal anomaly detection? Is the goal predicting failures, or is the goal predicting different failure types? So these are the type of questions that has to cross your mind, and you have to try to find a solution to before you can say, yes, this is a good use case that we should do, or no, it's not a good use case for machine learning. Let's look at an example of data quality. These are some plots that we see in real use cases. Let's look at the one on the left. X-axis is time, and y-axis is different sensors. These are sensor names. And each cell on this plot is essentially the intensity of the color indicates number of data points for that time period for that sensor. As you can see, there are a certain number of sensors that were recently installed at this time, for which you don't have historical data. The other observation is that the density of measurements vary across time. And as you can see, the dashed line here is a true positive, is a label, is a failure, is a known failure. And this is one of your failure cases. If you look at the two on the right, you can see you have 3 failures, but almost all of them are useless because there's not much data before the failure. So when it comes to creating features and learning from these models, typically we want to look back a certain period of time and see what led to the failure in our feature engineering efforts. And hence these 3 failures are completely useless. Let's go back to the use case scoping workshop and back to the question that was just asked a few minutes ago. Let's say the goal is to detect anomalies as soon as they happen before they lead to failure. So we want to do anomaly detection. What are the type of questions that you have to answer? Is one model per asset? Should I train one model per asset, or should I train one model across all assets if I have 50 assets? Do I need labels at all? If the problem is an anomaly detection, is not having a label a red flag for the project or not? Which are essentially true failure cases. Can I use known anomalies or shutdown events as a training mask? This is the other considerations that you may want to take into account. Now, let's say instead of anomaly detection, the requirements of the project is to predict failures n days ahead of time, n days before it happens. So you have a compressor, you have a turbine, you want to predict a failure 30 days before it happens. In this case, you probably want to have one model across all assets if you have consistent set of sensors and if you have similar failure signatures across all assets. And one of the requirements is that you have hundreds of known failure labels. So if any of these is not present, you probably cannot do a good job in predicting failures 30 days ahead of time. Let's look at another example where you want to have predict 3 types of failures. So not only one failure, but you want to predict 3 types of failure. So you probably want to look at training one model per failure type, or you want to have a multi-class classification problem. You want to make sure that you have consistent set of sensors across all these assets and similar failure signatures before each failure. And you may, in this case, you may want to have make sure that you have hundreds of known failure examples per failure type, not just 100 failure examples. So these are the type of questions, the type of follow-up thoughts that should cross your mind, and you should check with either the customer or your project team before delving into the machine learning part of the project. So let's say we do all of those and we start delving into the machine learning piece. We typically allocate between 5 to 7 weeks to the machine learning part of the project. And you might ask, we're talking about solving problems that were previously unsolvable. How can we do it in 7 weeks, right, or 5 weeks? And that has to do with what I will talk about in the next couple of slides. More importantly, it has to do with the power of the platform that you want to leverage to make sure you're not wasting your time on building the infrastructure, creating pipelines or creating plumbings behind the scene, and you're focusing only on the research problem, on the business problem, and implementing that. And that's why typically 5 to 7 weeks for us is enough, because we are, thanks to the platform, we can focus only on the business problem. Okay, as we know, machine learning algorithms are key. Okay, I believe that is established by now. But what is interesting is that they typically represent less than 5% of the code base. That is typically necessary to embed these machine learning algorithms into the existing process and essentially put them in the hands of the business users. What we do at C3 is that we take care of all the plumbings around the ML code so that the data scientists can spend most of their time just focusing on formulating the problem, implementing a quick prototype, tuning the ML models and the algorithms, and delivering more value to the business without having to worry essentially about all the rest of this picture, which is configuration, data collection, machine learning resource management, infrastructure monitoring, and so on and so forth. To do that, we cannot simply rely on open source tools. Open source tools for data science typically assume that you have some clean data as input, and that at the end you have a model, but it's your responsibility to put it in production. So the typical open source solutions only do the middle layer. However, to be able to provide a holistic solution, at C3, we have developed an AI suite that goes end-to-end. So from data management, going all the way to model management for when the model is in production and is making predictions live, to figure out, if you need to retrain the model, if you need to propose a challenger model, or you need to leave the model as is. So all the rest is essentially taken care of by the platform. Now, let's take a look at the steps that typically a data scientist takes to build a machine learning model from scratch and put it in production. As you can see, starting from the left, there is the data integration layer, where you start from the data management, start iterating on checking the data quality. You start with building machine learning features, and you prototype your models. At each stage, you may end up going back to the data quality check and even fixing your data acquisition script to fix any potential issues there might be with your data extract. Once you're happy with the model, you promote it to production. And C3 provides tools across this whole life cycle, and especially in functional areas where data scientists may need additional support that open source don't provide, such as data management and model operations. Also, we understand that data science is a very broad term. Some data scientists are comfortable with code, with high intensive code environment. Some are more comfortable with low code environment, and some comfortable with no code environments, drag and drop type of tools. And that's why those are all interchangeably available to data scientists. The other benefit that has enabled us to solve these problems in between 5 to 7 weeks, as opposed to 5 to 7 months, is that is C3ML Studio, where you start from a project, you start running experiments, you look at hyperparameters, you look at the results of your hyperparameter model, you pick the best model, and you deploy that to production, you scale it to large number of assets, and you monitor the performance of that model, all from the same user interface view. The other considerations that during the course of the machine learning part of the project, or as soon as you have machine learning models, is data visualization. It matters a lot. It matters when you are in the process of defining features. It matters when you're in the process of making sense of the predictions coming out of your model. Does the risk score or probability of failure make sense at this point in time? Let's cross-correlate it with this set of features and see if that makes any sense or not. The other very important consideration, especially if you're working with time series data, is managing information leakage. So oftentimes, the type of features that we derive have to do with looking back at certain period of time, creating some rolling window, rolling sum, min, max operations. And by doing so, it's very easy to lead information from the training period to the test period. And that way you're cheating. You may get exceptionally good results in the lab, but as soon as you put your model out in the wild, you get very bad results. So there's this buffer period that we always take into account and as a holdout to avoid information leakage. The other consideration is explainability. As we're going more and more towards deep learning models, they are known for not being very explainable. So if the requirements of your model is to provide explainability, you either should fall back to more conventional, more traditional type of models, such as decision trees and simpler models, or you may want to embed your machine learning model with an evidence package, and that's exactly what we do. We end up doing in projects. We want to make sure we use the latest and greatest machine learning models, but as I mentioned, they come at a cost of no or very little explainability, and that's why we end up appending evidence package in order to help the end user get a better sense of the results of these models. We use Eli5, Shapley, Turing Interpreter, and some custom feature importance modules that we have built. So let's say you have trained a couple of different models, let's say 3 models, and you're ready to promote them to production. And let's say your models are one-class SVM, Gaussian mixture models, and isolation forest, and they are creating more or less the same performance on the test data set. So you're happy with either performance of either. What are the other considerations that you may want to consider and take into account before essentially offering one to go to production? Here are a couple of things that we take a look at. Pre-processing or post-processing requirements. Let's say in this case, GMM is the worst because it doesn't scale. The anomaly scores doesn't have a min and max, and it can take any arbitrary value. While isolation forest is available in libraries, and also it doesn't need scaling. In terms of robustness to noise, we typically test all these machine learning models in terms of how sensitive they are to noise. In this case, one-class SVM might be very sensitive to noise. GMM might be somewhat sensitive, but isolation forest is not very sensitive to noise. In terms of complexity and computational complexity, one-class SVM might be complex in terms of if you use the nonlinear kernel, especially if you want to make a lot of predictions very fast across a lot of assets. You may want to make sure that the complexity is manageable, while isolation forest is again the best solution. Training data contamination. If you're talking about anomaly detection, it's very easy that there are some positive labels in your negative data set or as you're training. So how sensitive is this model to training data contamination? And interpretability and portability are the other things that we take into account. You may end up with a scenario where a model is great on all areas but one. And sometimes what we do, we tend to marry that with another module. Let's say in this case, isolation forest is not as good with interpretability. So we try to embed that with an evidence package, which I showed on the previous slide, in order to put the combination of two in production. Okay, I will talk about some open research problems before I hand over to Shouvik. Across the time as we've been working on these problems, there has been quite a few research challenges that we have been working on over the last several years. And also we have observed the community, the AI and machine learning community, to be concerned with. Small data, as I mentioned earlier in the talk, is indeed a big challenge. We are all familiar with big data, the term big data. In the era of big data, oftentimes we think that big data is a problem, but in a lot of industrial cases, in a lot of enterprise cases, where there's scarcity of data, limited number of labels and small number of training data points is indeed a big challenge. And Shouvik will talk about how we came up with an algorithm that can leverage knowledge from expertise in the learning problem. Very few positive cases or extremely imbalanced data sets are, in fact, a challenging problem that you have to be very careful. Interpretability, in terms of consistency of identity, separability, and stability of interpretability modules are increasingly important as we end up using more and more interpretability modules in our models and embed with the model. And also uncertainty estimation for deep neural networks. Deep neural nets, due to their sensitivity to model and data perturbations and their high capacity, tend to be very sensitive and high and sometimes uncertain. So estimating the uncertainty around the prediction is one of the areas that we are doing a lot of research on, and we are also looking at to the community. Embedding domain expertise knowledge will be talked about later today. And real-time optimization is another area where optimization of industrial processes via combining neural nets and first principle models is in fact arising to be a very prominent area of work, leading to staggering economic value for a lot of process-oriented businesses. And we're working on quite a few of these projects. All right, so that brings us to the halftime and time to switch to Shouvik to talk about automatic digitization of engineering diagrams and using deep learning and graph search, and expert-guided regularization, which is some of the work that came out of these predictive maintenance projects. We think of these as kind of two use cases that came out of this bigger picture predictive maintenance projects that we solved, and we had a lot of fun working on. So I would hand it over to Shouvik.
All right, thank you, Mehdi, for the introduction, and good evening, everyone. Thanks for joining us today. So I think Mehdi gave a good overview of who we are as a company, what we do, as well as a classic C3 application area, which is predictive maintenance, and how we approach these kind of predictive maintenance problems. So what I want to do today is I want to follow that thread and show you, two more problems that we've worked on, both which have been inspired from predictive maintenance, also applicable across the board to other application areas. And in the process, I also want to show you, a glimpse into our actual applications, as well as some of the tools that we have built at C3 and that we use as data scientists. So that's the agenda for today. Again, my name is Shouvik. I'm a teammate of Mehdi's and work on the data science team. So let's get started with this first problem, which is the automatic digitization of engineering diagrams. So what do I mean by that? Well, you might have gotten a sense from Mehdi's talk that C3 works in a lot of asset-intensive industries, right? So, we work with a lot of, very physical assets, right? We're talking about things like, a paper machine at a paper factory, or a steam turbine at a power plant, or, oil and gas refinery, right? Some machines, right? So what we found when working with a lot of these industries and a lot of our customers is that a data source that's used universally across these industries are engineering diagrams. So what is an engineering diagram? Well, an engineering diagram is a representation of the layout of an industrial facility. So one way to think about an engineering diagram is an engineering diagram is to an industrial facility as an architectural blueprint is to a building, right? So what you'll see in any of these diagrams is, you'll see a whole lot of symbols and lines and text. And what it's doing, it's representing this facility and saying, which assets are in this facility, which assets are connected to other assets via these lines. What is the flow in the facility? So the direction of, say, current, right, or of direction of fluids. It also has a lot of textual identifiers. So text all over the place describing these assets, or linking them to some operational database or enterprise data systems. So that's kind of what you see in these diagrams. And don't worry, I'll show you many examples in just a moment. But what I'd like to do is just go over how these diagrams are used. And they're actually used throughout the life cycle of these industrial facilities, right? So they're actually drafted in the design and construction process, right? So they're put on paper and they're revised. You also see them being used in operations during maintenance. So maintainers will go into these facilities using these diagrams as maps, essentially. And they're also important for safety checks, right? So they're used in these safety quality assessments. In fact, what we find is that in many jurisdictions, there are legal requirements to keep these engineering diagrams up to date because these diagrams dictate what kind of actions can be safely taken in these facilities, right? So it's a matter of safety, right? It's a big deal. And all of these factors combined, you get a sense that, yeah, these diagrams are a very important ground truth data source for these industrial facilities. And these companies need to use them. The problem with these engineering diagrams, though, is that they're just diagrams. And you can imagine for any industrial facility, let's say oil and gas refinery, you can have thousands of these documents per plant, and it's a very tedious work to actually maintain these diagrams and keep them up to date. What I've seen from my experience, so recently before the pandemic started, I was in Saudi Arabia, and we were at an oil and gas facility, and these guys have millions of these engineering diagrams, and they're all locked away in shelves. And anytime these maintenance people want to have a look at say what assets are in any of my facilities, they have to go through these diagrams, peruse them one by one, and do this intensive manual labor, right? We've had another case, industrial manufacturer in Europe, which has a team of 50 people whose job it is to digitize these diagrams because they're so valuable to these companies. So we work in this enterprise AI space. So we thought that there must be a solution to this. So what I want to present today is a solution to this problem and an application that we're building around the solution. So going into more detail, this is an example of an engineering diagram called a piping and instrumentation diagram, P&ID for short. So what you can see in this diagram is you see a lot of funny looking symbols and lines and text, and we'll go into detail into what they mean. But at a high level, the way you can think about this is each of these symbols represent some asset. So specifically these big symbols you see over here, they represent equipment. So equipment could be a pump, or in this case, it's a vessel, right? There are also a lot of smaller symbols that you see. And usually smaller symbols represent instrumentation, so sensors, for example. You also have a lot of funny looking triangle symbols that you see here, lots of triangle symbols. And those are actually valves. So very familiar to Mehdi, who has worked on predictive maintenance for valves for one of our largest customers. But you see valves everywhere in these facilities, right? So you can see that these diagrams are teeming with knowledge, right? With all of this information, of all of this great domain expertise, that if we could pull it out, it could be of value to these process engineers as well as of value to us data scientists, right? Who can build applications on these diagrams and on this data. So to give you a sense of what's possible, right? Imagine if I were to digitize these diagrams and extract the assets in these diagrams, the relationships between assets. So what asset is connected to what other assets, the text of these assets, and the lines connecting them. Imagine all the things that could be possible. For example, you can enable diagram search across thousands of your diagrams. You can search for very specific equipment and instrumentation. You can enable this process that we called equipment and sensor mapping, right? So you might imagine in a predictive maintenance project, let's say I wanted to do predictive maintenance on this piece of equipment. I might want to know which sensors are connected to this equipment. What we've previously done, even at C3, is go through hundreds of these diagrams and actually look and see, oh, okay, this sensor is connected, this sensor is connected, this sensor is connected, because they're close by to the document. And then we pull the actual telemetry data, right, from those sensors and do this kind of joining before we can train our models. But all of that can happen automatically, right, if we could digitize these diagrams. So it just opens up a whole new set of possibilities if we can take these very say basic diagrams of physical facilities and convert them to digital representations. So that's what we're going to try to do here. And specifically, we're going to try to address 3 problems. So number 1, detecting the symbols. like this, and like this. Number two, detecting the text and associating them with the symbols. So text like here. And number three, detecting the connections between the symbols, right? So you might imagine, this symbol is connected to this symbol. So things of that nature. Let's zoom into this diagram, and I want to teach you a bit more specifics of piping instrumentation diagrams, which I said is one kind of engineering diagram. So in this cross section of the PNID, you see many different kinds of symbols, right? So the first one I want to point out is this circular symbol, and this is called an LMI, a locally mounted instrument. And this typically represents a sensor on the field, right? So LMI could be a pressure gauge, or it could be a temperature indicator, right? So it's collecting data. What you'll typically see is that these LMIs are connected to these funny looking symbols, which are these circles inscribed inside these squares. And these are called tags. Tags are one way to think about tags is they're the digital representation of these sensors, right? So
question. Are there only PDFs or printouts you have available to start with, or do you have the actual CAD files that you could read that actually have structure in the files?
That's a great question. So sometimes you do have CAD files. Sometimes you just start out with PDFs. In rare cases, yeah, all you have are printouts, right? And these are nasty legacy drawings, right? I've looked at drawings from the 60s and the 70s. In which case, sometimes the standards are even different, right? Like what the symbols used to mean back then don't mean the same thing anymore, right? So it's like a nightmarish scenario to look at these diagrams and try to parse them by hand. Even when you have them in CAD format, they come with very limited metadata and not the fidelity that you might like. So the most common use case that we've identified is just taking these diagrams in PDF form and extracting all the information out of it. So then, continuing with this PNID details. So again, these circles inside the squares, they are tags. And typically they're this digital representation of the sensor. And what that means is that often you have some sort of operational historian, like a Pi server, which is essentially time series database. And what you can do in that Pi server is I don't know if you can see the text inside the symbol in this resolution, but what you can do is you can take that text inside these tags and you can do a lookup on the Pi server, and you can actually fetch the time series telemetry data that is coming off of this LMI sensor, right? So again, this is the value of this kind of application, is you can actually link your engineering diagrams, these are physical facilities, to actual time series data that you have. And these data sets were siloed before, so you couldn't do that before. So these are the two symbols that are of interest to us in this work. We also have, as I said, bigger symbols like equipment. And at least at this point, we haven't looked at actually detecting equipment yet, because there's a lot of variance among these equipment. You can imagine a whole lot of equipment, and they look sometimes similar, sometimes different. So that will come in a later phase. What you'll see right now is we've manually labeled these equipment. They're still important to us. You won't find as many in these diagrams. So we can just manually label them through a drag and drop tool, or through our UI in our applications. So those are some of the symbols. The other important element in these diagrams are these lines. You see them everywhere. What they are is, they represent the flow of sometimes information or of sometimes materials. So these solid lines are called the process lines, and they indicate actual physical, say, pipes, for example, right, that carry fluids. You also notice these dashed lines. And these dashed lines represent electrical signals, which is why you'll often see these dashed lines from these LMIs, which are again sensors, to the tags, which are these digital the digital equivalent of these sensors, right? So that's in a nutshell what these diagrams contain and what we will be mining out of these diagrams. And to put this work in context, we have found this use case come up across many of our customers. So what we often do in that case when we see a generalizable application like that is we build a SaaS application around it. So currently we're in the development of C3.ai digital twin, which will be an application that will ingest all of these diagrams, as well as 2D and 3D CAD drawings. It'll also ingest simulation data, right? So imagine the possibilities if you can connect simulation data that you have with your facilities and with your diagrams. So it will ingest all of these data sources, as well as typical C3 data sources like work orders, describing maintenance on equipment, as well as other external data sources. So we're thinking about weather and through third-party APIs, and integrate all of that data sources into one federated image. And the application we're building around that, this is the C3 AI digital twin. I just want to walk you through what that is going to look like. What you see over here is, this is kind of a standard view of what a typical C3 application looks like. You have, if you think of our customers, they are mainly industrial customers. They have, again, a lot of assets. In this case, these customers will have a lot of facilities in these organizations. So what you're seeing here is the landing page of this application, in which user can see all of the facilities that are under their management. So here you see we have the steam cracker facility with 100 diagrams. Maybe we can drill down into it and see what's in this facility. What you see here now is a file view, a tree view of the elements in this facility. And the way we approach this, we think of this in a systems of systems view, right? So you may have a steam cracker facility. This is your highest level. Inside that, you may have a gas compressor system, which may contain a turbine. And there may be multiple piping and instrumentation diagrams, P&IDs, which contain this turbine. So that's what you see over here in blue. This is an important view of our data, and this will keep coming up again and again. This is what we call an asset hierarchy. This asset hierarchy will be used to structure the data and hold the data as we extract the elements out of these diagrams. So next, let's drill down into one of these diagrams and see what this application will let us do. So what you see is, we've selected one diagram. And you see here in these colored bounding boxes are the predictions made by our machine learning model. Right now, this model is predicting between two types of symbols, tags and LMIs. So again, tags are the circles inside the squares, and LMIs are the circles. So you see here is picked up all of the tags. And it's also giving us a measure of confidence or uncertainty in these predictions. As well as text that has been extracted out of these documents and that's been associated to these symbols. So that's one view. One thing we realized is that no matter how hard we try, our model's predictions are not going to be perfect, right? Especially when you have these very messy data sets. So what we realized it's very important to have an application that supports human in the loop, right? To let the user validate these predictions and verify them and mark them as correct if necessary, or to make their own bounding boxes around symbols that are of interest. So this is a mindset with which we approach a lot of problems, but especially this problem of a digital twin and engineering diagram digitization, because there is this margin of error, right, in our models. So this is what the application will look like. I'm sure you're more curious about the actual, the machine learning that's going on, right? So I'll just start with an overview of our machine learning pipeline. I'll show you a demo and then we can go into details. So how this pipeline works is, as input, we take in P&ID image. And we also take in some manually labeled symbols, right? So if you remember, we said that in this phase of the work, we're not looking at equipment symbols because they're hard for us at this point to detect. So we'll just let the user specify where the equipment are, and we'll take that in as input as well. After that, our pipeline has 3 steps. First, we'll detect all of the symbols in the diagram. And by symbols, I mean specifically the tags and the LMIs. Then we will associate, we'll detect the text in the diagram, and we'll associate the text to the symbols. And then finally, we'll detect the connections between the symbols. And we'll create a graphical representation of which symbols are connected to which other symbols. As output, what we'll get is this asset hierarchy that we talked about, which is this, in essence, it's this digitized representation of the diagram. So what you see here is, for each symbol that has been detected, we know whether it's been manually labeled by the user or whether it's been detected by the model. We get to see the type of equipment, whether it's an equipment, a tag, or LMI. We'll see the associated text with these symbols. And finally, we'll see symbols that are connected to these symbols via lines in the diagram, either solid lines or dashed lines. And this will be, a table that we can feed into some relational database, right? Or at C3 we call this our type system. So this is our proprietary way of storing and representing data. And then you can imagine you can actually build intelligent applications off of this representation. So with that, let me jump into a demo in a Jupyter notebook, where you'll get to see both the approach as well as the backend behind the application that you just saw, and our way of developing that backend. Before I jump into that, just want to take a break and ask if there are any questions on the problem as a whole, or what we're trying to do over here.
Yes, there was a question in the chat. Are you able to see the chat?
Oh, okay. Let me check.
The very last one in the chat, which says, why not just read the control panels in the operations room? I used to update these. Most of them are out of date. How do you relate these to the as-built flow?
Sorry, how do you relate them to the what?
As built. In other words, the way it actually exists in the plant.
Yeah, I think that's a great question. And that's actually part of the problem, right? When dealing with these diagrams, is that things in these facilities move around, right? And they change. And these companies have a very difficult time keeping these diagrams up to date, right? So what change is not going to be instant, right? This application isn't going to fix all of the problems with these outdated diagrams that we already have. What it'll do is it'll make life easier, right? The way we like to think of it is, if it can take out 80% of the burden in this intense manual labor, then say the 20% that opens up can be devoted to these tasks, like finally being able to upload or update those diagrams that are still hanging around since the 70s, right? So that's one way of thinking about it, and that's our approach as well. Oh, I can see this Q&A now. All right, here we go. So one person is asking, is the output of your process a nice CAD diagram in a digital form that can be used by a customer using some popular CAD tool or something else? That's a great idea. That's something we actually haven't thought about. What if we can actually output, take this digital representation and output a nice CAD diagram. In fact, that could be great for a lot of these legacy drawings, which don't even have CAD files, right? They were either hand-drawn or, their CAD files have been long lost. And so actually I haven't thought about this, and this is a great idea. So that's something I'll bring back to our product team. How about that? All right, so I think I know you all want to see some software, so let me just jump straight into the demo. And if there are any other remaining questions, we can take them at the end as well. Just give me a second. I'm trying to share my screen over here. Computer is just hanging. And my slideshow. Oh, just stop the share. Okay. All right. Do all of you see a nice Jupyter notebook here?
Yes.
Perfect. Okay. So we're on the demo then. What you're looking at over here is what we call a C3 containerized Jupyter notebook. So most of you are probably familiar with Jupyter notebooks. It's a data science rapid development and prototyping tool. At C3, what we've done is we built our own extension of the Jupyter notebook that is hosted on C3 servers and has very tight bindings with our C3 software, right? So one very simple way to think of C3 is it's a platform, so it's a box, and it has a lot of data in it, which we put in it, say diagrams or time series data, and it has a lot of functionalities, pre-built functionalities that either come with this box or you could build into this box so that you can develop and deploy these AI applications. So that's most important to us. So what you're seeing here is what a data scientist at C3 would typically go through to develop their models or their algorithms and deploy their solutions in an instant. So I'd like to walk you through that. So first, just as with any Jupyter notebook, we'll just load in our libraries. So some which you'll be using in this notebook, and some which you don't see because we built it into the C3 software. So let's get started with that. And also, before I start the demo, let me show you what data sets I'm using as an input. So let's look at our data here. And the data that we're starting with is, seems to be lagging a bit, but here we go. So we're actually just starting with two pieces of data in this demo. The first one is our actual P&ID diagram. Zoom out a bit. And this is the same diagram I showed you in the slides. And this will be the diagram that we'll parse in this demo. We also have a set of manually labeled symbols. So remember, I showed you those green symbols, which I said are too hard for us at this point. So we'll just ingest them as bounding boxes given to us by the user, which you can imagine very easy to draw in a UI. And that's what you see over here. So for each manually labeled symbol, we've provided bounding boxes around the symbol. Think of this as some starter symbols for a model to start with. So once we have that, let's get started. First, what I'll do is I will load in this P&ID diagram that I just saw, P&ID diagram.png. And what you see here happening is that you see we're calling a C3 module, and we're calling a diagram utils class on it, and a load and process diagram image function. What's going on over here is we're utilizing what we call the C3 type system, through which you can expose both data and methods. It's a very nice object-oriented approach to doing data science, right? And it's a nice combination of this object-oriented programming and relational databases. So in this diagram utils type, I've exposed this these methods, and this is what you'll see throughout the demo. Is most of the methods that I call are not actually in this Jupyter notebook. They're actually in the C3 server. They're deployed there, and I'm just making calls to that. So this is our input diagram image. Let's also load in those manually labeled symbols that we saw. And what we do is just after loading in the manually labeled symbols, we create this asset hierarchy data structure. And this is an essential data structure, as I said, in our application. Right now, it's mostly empty because we actually haven't mined anything in yet. All this asset hierarchy contains at the moment are the manually labeled symbols. So for each manually labeled symbol, you see one asset object, and you see one bounding box, and that's all you see. And you have a couple of manually labeled symbols. But as we go through this diagram digitization pipeline, we're going to fill out the associated text, and as well as symbols that are connected to each of these symbols. Here's a nice tabular view of the asset hierarchy as soon as that loads. So here we go. So what we're saying here is, so far all we know about this diagram is we have 5 symbols in here. They've all been manually labeled, and they're of the type equipment. And we'll just quickly display what we have so far. And what we'll do in this demo is we'll grow this asset hierarchy table both vertically in terms of more symbols that are detected, as well as horizontally. So in terms of text that we extract and some connected symbols that we mine. And so again, here is just take the diagram image and we just overlay the manually labeled symbols that we're starting with. Okay, so this is our starting point for our demo. We've just loaded in all of our data. Next, we'll actually start the fun part, which is this automatic digitization of this PNID. What you're looking at over here is a convolutional neural network, a CNN, that we use to classify 100 by 100 pixel crops of the image. So what we're doing here, and I'll get into more details after this demo, is we're basically slicing and dicing this diagram. We're sliding through it, and we're extracting these 100 by 100 crops. So a crop might look like this. And we're passing it through this CNN. And we've trained the CNN to predict from a given image crop whether that crop contains one of 3 symbols, right? So here you see this final output layer is a 1x3 softmax layer. And this layer predicts the probability that there is, number 1, tag inside this image, LMI inside this image, or there's no symbol inside this image. So it's a very simple setup. But there's a lot of, this is just the model, right? There is a lot of work that goes into, sliding through this diagram, running this model, collating all the results, getting rid of, overlapping predictions through non-max suppression, thresholding. So a lot of work. But what we've been able to do because of the type system is we've been able to abstract that through the symbol detection pipe. So this is an artifact that lives on C3 server, which we're initializing, much like class. And this will enable us to actually do the symbol detection. So what you're seeing over here is, this is our actual underlying model in the symbol detection pipe, the CNN model. So this is implemented in Keras. We've trained it in Keras. And what you see over here is Keras pipe. So this is C3's Keras integration. Makes it very easy to deploy Keras models, as you see over here, right? So we have a model deployed and we just get that model, that's it. And we also have some other, I wouldn't call these hyperparameters, I call these settings, right? We have some settings that we like to use in our symbol detection. So you see, we're saying that in this network, our first class in the output is the tag class. And we'll use a classification probability of 0.95. Same for the LMI, right? But this class is class 2. And we initialize the symbol detection pipe with our underlying symbol detection model, as well as these settings, right? And you see there are several other settings here for sliding window sizes and sliding window strides, some non-max suppression settings. And I've run this cell already. And what you'll see here is what we create here is something we called a diagram and asset hierarchy. And all this is doing is it's taking the diagram image, this PNG, and this asset hierarchy, this table that we've set up over here. And they're combining them into one input so that we can process it through the pipeline. Once we do that, the cell I've just run, it's taking the symbol detection pipe and it's calling process on this pipe with the input that we've defined in this cell. So one way to think about this pipeline, right? We have these multiple steps. And at each step of the pipeline, we're carrying over the output from the previous step. So at this point, all we have are, is this diagram and asset hierarchy. So we're just taking that in. And the output is also a diagram and asset hierarchy, but it will have more symbols and it will be more complete. While this runs, let me just, so it'll take maybe a minute or two to run. Happy to take any other questions in the meantime. I can also tell you some stories, So, as I said, we've done this previously manually, right? And we've had a use case where we had oil and gas plant with a lot of these diagrams, and we were trying to do unsupervised predictive maintenance on these diagrams, right? So we had a big team, but what we had to dedicate is we had to dedicate 2 people just to go through these diagrams and just by hand manually extract all these symbols and extract the text in these symbols. And it was a pretty brutal process. So it was their experience that in some way inspired us to build this application, and that's what you're seeing over here. So as I finish the story, you see that this cell has just finished running and has given me my diagram and asset hierarchy. So let's see the results. Let's see what it looks like. All right. So this is the fun part. What you're seeing over here is in green, you're seeing what you had before, manually labeled symbols. In red, you're seeing the symbols that have been detected by our machine learning model, by our CNN. So you see overall, it does a pretty decent job, right? This is an LMI. This is a tag. LMI, tag. So, wonderful. You also notice it makes a few mistakes, right? This is not LMI, okay? LMIs are circles, they're not ovals. So, I get the sense here that maybe our model is not robust to certain variations in shapes, certain transformations. This is not an LMI, right? So this funny looking symbol with like circle with 2 circles inside, no, that's not an LMI. That will not fly with these teams. But again, remember, that's why we need to keep in mind a human in the loop interface, right? These predictions are not going to be perfect. They're going to be 80–90% solutions. And I think the novelty and beauty here is that we're going to let the user correct these mistakes and draw their own bounding boxes. You also notice some false negatives here. This is an LMI. It should have been detected, but for whatever reason, haven't been able to detect it. So, see, just with one step, the symbol detection step, we bring this diagram to life and we expose all these symbols. What you see over here is a cell I just ran. And this cell, as I said, I promised we'd be vertically growing this table as well. And that's what we've done. What you see over here, you start label symbols. And now we have been able to detect all of these symbols that you saw in red. So, and you see that some of them are actually tags and others are also LMIs, right? So that was our first step in digitization. We detected the symbols. Now, as I said, the value of this diagram digitization, no one really cares about detecting symbols, right? It's like, so what, right? The real value is being able to tie them to operational systems and enterprise data. And the missing key there is the text. So the text is a crucial element in these diagrams because, as I said, what you can do is once you have the text, it's a key identifier. It's a unique ID essentially, and you can look up data from that tag by using that text in say a tag as a lookup key in your time series database, right? So that's how these systems are set up, but they're disjointed. So using this text detection and association, we'll finally be able to bring these data sets together. So what I've done here is I've loaded in a pre-trained text detection model called East text detection. So it's a pre-trained neural network. And again, you see we have another pipe in here, a text detection pipe. This pipe takes we initialize it with the model, the text detection model, and again, another hyperparameter. But when we call process on this pipe, this process function, again, it takes in this diagram and asset hierarchy, which is our data set, our asset hierarchy that we're building. And it also gave me back a diagram and asset hierarchy. So now we're going to continue. We're going to see what this asset hierarchy looks like. What is the text that we've extracted out of these diagrams? And we see that we've extracted quite a lot of text. And some of it makes sense, words like note and fill. Others don't make so much sense. So I don't know what rubriquette is. Looks like some parts of the word get cut off. You also see a lot of text numbers, which may not make sense, but those are actually key identifiers that you could use to look up these symbols in the data, and time series data. Tubing. Okay, so some text makes sense. But let's see if we can actually point to those pieces of text in the diagram. And another useful activity is looking at the relationships between the symbols and the text. So what we're saying here in this asset hierarchy is we're saying symbol 0 over here has all of this text associated to it. And let's see if we can find those texts in the diagram. So note TK8 8303. Let's see if we can find some of those. Let's zoom in. So our symbol 1, where's symbol 1? Ah, okay, so sorry, that was symbol 0. This is symbol 0. And you do see some of those letters and numbers. So you do see 8303. That's something we saw on the table. You can see over here, very small letters. I don't know if you can see it, but I can see it. It says note. Actually, there's note over here as well. So we do get a lot of matches. And then you see why we make some mistakes as well, right? So for example, like there was a word in the diagram called lubricator, and we just caught the first part of it, right? So I'll be honest here, and we've been honest to ourselves that text detection in this application is our biggest area for improvement. And we're looking for some good off-the-shelf solutions out there right now to both detect these text regions as well as to parse them, so to do OCR. So this is a nice view of the text. What you're seeing in blue, you're actually seeing the regions of the text that have been detected by yeast. And then what we do is we do some post-processing and apply OCR. And it's very clear where the failures are happening here, right? So you see that the reason we found lubriquette, CAT, in there is because it was not a fault with the OCR, it was a fault with the text detection step, and it cut off the entire word. So there's some work to be done here, and then we'll do that going forward. The final step in our pipeline is a step that I'm most excited about, and I think is the most novel part of our work, is this connection detection pipe. And again, connection detection is the process of detecting which symbols are connected to each other via dashed or solid lines. The way we implement connection detection is not through object detection like we did for the symbol detection pipe, but through a novel graph search methodology. Now, I'll get to more details on that in just a moment. I'm not going to run this cell because, as you can see, the graph search does take a while, but I'll just go through the results and walk through them with you. So again, we have a connection detection pipe, takes in the diagram and asset hierarchy, returns the diagram and asset hierarchy, and we take that asset hierarchy that we get back, and let's look at it in a tabular view. So what do we see over here? Well, we have a new column now, connected symbols, and now it's been populated. And what you'll notice is for each symbol, we have the IDs of the symbols that have been identified as connected to that symbol. So we're saying over here, it's essentially an adjacency list. That's what it is. So we're saying that symbol 3 is connected to symbol 5, 7, 9, 14, and so on. And so, over here, what we've done is we've just mined the interrelationships in these diagrams. So now if you wanted to know, hey, what are the sensors connected to equipment 3? It's already done for you. And to power your predictive maintenance application, maybe you just want to fit a model that is trained on data coming from these sensors, right? So that's one approach. So let's look at this symbol now in the diagram, and let's see if these connections are actually correctly mined. What you're seeing over here is a a look into how this connection detection is actually implemented using this graph search methodology. So symbol 3, our source symbol, is shown here in red. In blue, what you see is you see all of the lines that have been traversed by our graph search as we start our search from symbol 3 and traverse through the diagram. And in green, you see the symbols that we hit in this graph search process. So what we're saying over here in this case is that the symbols in green are connected to this red symbol. And we can do that for all other symbols. This is essentially, it's like an explainability feature. This explains why we detected all of those symbols as connected to symbol 3. And we detected symbols like 5 is connected, 9 is connected, you see that, 27, and you'll see those same numbers in that table view. So you see symbol 3 is indeed connected to 5, 7, 9, 27, and so on. Okay? So that pretty much wraps up all of the individual steps in our diagram digitization pipeline. And we probably got the sense so far that this is how we think about machine learning at C3. We think about them. We think about machine learning in terms of pipelines, right? Very similar to say scikit-learn pipelines that maybe you're familiar with. I guess I didn't run that cell before. So that's not defined. But what you can do once you have these pipes, individual pipes, is that you can string them together in a pipeline. And this pipeline is now an artifact that you can actually deploy on C3. So when I showed you the application previously of the whole C3.ai digital twin, it will actually be using this pipeline. This pipeline is the backend. Once we have this pipeline, we can use this pipeline to process data through the entire pipeline, through each of the pipes. And then finally, we can upsert or push this pipeline to our C3 server. So now other data scientists can use this, and our SaaS applications can use this. So this is a glimpse of what data science development and AI application development looks on the C3 AI suite, and how we power essentially all of our SaaS applications. This is how we build stuff at C3. So I'm going to wrap up the demo with this. Now I want to go back to the slides and get into a few details of how we actually implemented a lot of these pipes. Let me just share my other screen here. Okay, so I actually have a question over here. The question is from Karam, and he's asking, does the model detect connection in terms of inlet-outlet, upstream, downstream, for flow direction or similar manner? Okay, that's an excellent question. So by inlet-outlet, upstream, downstream, what I assume you mean is the actually these the diagram. And this is the symbol we didn't go over, but it's definitely an important symbol in these PNIDs. And what they allow us to do is they allow us to connect one diagram with another. So you may see over here, you may see an inlet symbol going into this diagram, showing flow coming into this diagram. And on another symbol, on another diagram, you may see a corresponding outlet symbol. And the way you can join them is using the text inside these symbols. So excellent question, Karam. And right now, we don't detect those connections, but that's that's on our radar, and that's something we want to do. Because again, as I described, we have thousands of these diagrams per facility, and you don't only want to be able to discover relationships and assets inside individual diagrams, but across diagrams as well. So we're in the process of doing that. So very quickly, I'll just go through some of the work we did to actually train these models and to set up this pipeline I just showed you. Back in January, this whole project was developed in a couple of months. And back in January, we started this process of labeling our data. So we had a collection of PNIDs, and we just sat down, and for hours we just labeled all of the tag symbols and the LMI symbols. So this is just showing our training set where we had almost 1,000 symbols labeled. And then we also automatically, we just took random samples of not symbol crops, which didn't contain tags or LMIs. And these are some of what the crops look like. And this is what this is the data we used to train the CNN that you saw earlier. Okay. So that's the symbol crops, one data set we collected. The other data set that we labeled are these equipment symbols, which you all saw. So then once we had these symbols, labeled, we trained the CNN, as you saw before, relatively basic CNN, I would say. We did some hyperparameter tuning here in architecture search. So we tuned the number of layers, the number of filters and nodes at each layer. And we also did a lot of work on data augmentation. So that improved results a lot. And then we tuned certain hyperparameters like dropout and batch norm. So that's kind of our process of training this model. Once we had this model, again, the model wasn't everything because it is a diagram and the model is just detecting symbols and crops. We actually took a sliding window approach where, we had this 100 by 100 sliding window and we slid it over the diagram. And, for each window, we ran the window through the model that you just saw. And for each of those windows, we actually said, does this crop have a tag, an LMI, or does it have nothing? So once we did that and we post-processed the output, what we got are the symbols, the detected symbols that you saw previously. So both the tags and the LMIs. These are the results that you saw before from our text recognition steps. So just to recap, for text recognition, we use a combination of EAST, pre-trained network for this text detection, and then we use Tesseract for the actual text parsing. And finally, I want to quickly go over our connection detection approach, through which you saw those fancy lines showing the interrelationship between the symbols. And again, connection detection is this problem of detecting solid lines, or rather detecting connections through solid lines, or detecting connections through these dashed lines. And again, the way we approach this is, I'd say, a non-traditional way, right? So we took this image and we decided to convert it to a graph. And what do I mean image is a graph? Well, what I mean is, so an image is just an array of pixels. What we said is we'll have a node for each pixel. And the node will contain the information of whether the image, the pixel is black or white based on a threshold. And the node will also know, what symbols are present at that pixel. The edges in the graph, so basically there will be an edge for each adjacent node, colored nodes. So there will be edges between all of these, colored symbols, but there won't be an edge from, say, this pixel, this node, to this not colored node. Once we have represented our image in this way, what we can do is we can actually start a graph search from each of these symbols. So, if I pick this symbol and I start a graph search, a depth first search from the symbol, and traverse through the lines of the diagram, through the nodes of the diagram, I'd be able to hit this symbol over here and this symbol over here. Right. So right now we're just limiting to first degree connections, but we can change that in the future. So as you can imagine, a challenge here is, you saw a lot of those dashed connections, right? If you represent the diagram in this way, suddenly, your graph search, your depth first search can't go through these dashed lines because, as I said, there are no edges between, a colored circle and a non-colored circle. So the way we solve this problem is by pre-processing this graph and actually solidifying, filling in these lines. So first we detected those dashed lines using a technique called probabilistic Hopf transform. And then we just filled in those lines, filled in those nodes. And now suddenly you can actually do a graph search where, if you start at this symbol, you can definitely hit this symbol. And you can also hit this symbol as well, both solid and dashed lines. And so now the results I showed earlier, they'll make more sense, right? These lines are that traversal path. when you start, these blue lines are the traversal path. When you start at this red symbol, and the green symbols are the symbols that you hit through these traversals. And you notice here, there are a lot of these dashed lines that we're able to traverse through. So over here, as I said, this is a connection between a LMI and a tag. So it's obviously a dash line. And you see that we are able to traverse through these dash lines. You also see a lot of funny behavior, right? So you see a traversal that goes all the way out into this inlet symbol. So it seems like our graph search is very hungry there, trying to find some lone symbol, but it doesn't. So it comes back in this path and finds some other symbols and satisfies itself.
You use some constraints on the Hopf transform, so you just look at where there's a starting dot on the edge of the object, like the red object or the blue object.
Mm-hmm.
And that way you don't search across every combination of pixel to pixel if there's blanks and stuff.
I'm sorry, Greg, can you say that again?
Go back to slide 60.
Yeah.
So where there's the red box and
Mm-hmm.
you inferred there. So I guess you assume that there's going to be a pixel on the dashed line starting next to the red box, or you're just using the probabilistic Hopf transform. So you're not applying that everywhere. Are there some kind of constraints where you apply that?
Yeah, that's okay. So that's a great edge case that you just found out. So it turns out that this probabilistic Hopf transform, it does handle that edge case to a pretty good degree. So you're talking about the situation where if there was no black dot right next to the symbol, right? How would you be able to go through? So it turns out that we can still detect the dash line in that region and are still able to reasonably fill it in. What I'll also say though is these are heuristics at the end of the day, right? And at this point, that's the best we can do. And we also found that these techniques are very sensitive to the hyperparameters. So a problem we're working on right now is maybe a certain set of hyperparameters for a certain set of diagrams works very well. You can detect those dashed lines and you can traverse through them. But maybe it doesn't for another set. That's the reality. So again, it's this human in the loop mindset, right? So we are building an application that will let the user tune those hyperparameters to get their desired results. And that's not just a machine learning problem, right? That's the user interface problem, right? How do we expose these knobs and controls to the user and empower them, right? Instead of confuse them, which we can risk doing. So after connection detection, our pipeline is complete and we've been able to digitize this diagram. And that's great news. I'm sure this is great news for all the process engineers in the world who are out there and all the maintainers. Just a quick look at our actual results. So remember, we had 18 diagrams in our training set. And we labeled another 11 diagrams in our test set. Same kind of labels, tags and LMIs. What you see over here are the precision and recall curves for this evaluation experiment. The solid lines represent our actual test set performance, and our dashed lines represent our training set performance. So these blue lines are for the tags, and the orange lines are for the LMIs. And what you notice over here, and if you look at actually the scale of the graph, we're doing a pretty decent job. And we're able to get almost perfect classification for tags. And we're able to get reasonable classification, over 90% precision and recall for the LMIs. And you also see that we're not overfitting, right? Which is nice. The curves don't always look like this. So we had to take a lot of steps to actually get to this process. So, for example, data augmentation. For example, reducing to simpler models. Those are some of the steps we had to take. Another step which you might not expect. When we're first, starting out, we were just looking at classifying tags, right? These circles inside the squares, and we're getting pretty poor results. We're getting around 70% precision, 60% recall on just that symbol. And when we actually looked at the predictions, it turned out that our model was getting confused between tags, these circles inside squares, and LMIs, which are just the circles. So then we actually labeled our whole data set with those LMIs. And then when we introduce this differentiation between these two symbols, then our model, would get less confused between these two symbols. And we noticed that, our tag classification went up, significantly, almost perfect classification, because now this model wasn't getting confused between tags and LMIs anymore. So that was a great discovery for us. This is another view of the results. So this is showing for the diagram that I showed you before. So this is actually one of the diagrams in our test set. We're looking at the ground truth symbols that we labeled manually in green, and the symbols that have been detected by the model in red, as you saw before. And you see over here, there's pretty good overlap, right? This is something we'd be happy with. And you see some false positives, as I said, here, here, and a false negative over here. So to wrap up, we believe this diagram digitization pipeline will enable the next generation of industrial AI applications. So starting with simple things like just diagram search, being able to search, which components or which assets are in which facility. What is the time series data coming out of, this sensor over here in this facility. So simple questions like that will be easy to answer. And then you also have more advanced questions that can be answered. Say, let me fetch all of the time series data that are coming from sensors on a certain equipment, right? This is this equipment to sensor mapping process. So with this process, what we'll be able to do is we'll be able to create what we call this digital twin, these digital representations of these facilities, and it will be a great asset for these process engineers and maintainers who have to work on this day to day. So with this, I'll wrap up our presentation, and I'll open it up to questions. So Mehdi, if you're still on the line, I think both of us would be happy to take your questions at this point.
Yeah, I may present one more slide on the lesson learned, and then I will close if you don't mind. Yeah, and we will have plenty of time for questions. All right. Thank you, Shouvik. I hope you have learned something over the course of the last almost 2 hours. These are some of the lessons that we have learned working on such problems over the course of the year, which we would like to share with you. First of all, be very careful about selecting the use case, as I highlighted in the beginning. Not every problem is solvable or is solvable to the degree that is required. There are, in the case of predictive maintenance, for example, there are cases where failures are either unpredictable or unavoidable. So we want to make sure that you set the expectations right before delving into the problem. Don't raise expectations too much, or try to manage that, as the success of this project and on upcoming projects will be dependent on the success of the early success that you can get on this project. Do not underestimate the effect of data quality in your ability to solve the problem. There's been a lot of cases where the data quality has hindered the ability for us to solve the problem to the degree that we would have liked to. And we've had to resort to some other data sources or other ways to augment the data set in order to improve the overall data quality. So data quality is extremely important. Make sure to implement closed loop feedback from the field to enable continuous learning. There is a wealth of information in the data that is coming from the field, especially the feedback that you're getting from the field by implementing the decisions from your AI model. And it's extremely helpful to take those inputs, integrate them into your learning problem, and continuously learn and be able to improve the performance of the model. Make sure to implement human-in-the-loop frameworks. As Shouvik was showing in one of the applications that we've built, namely digital twin, the human in the loop has enabled us to leverage this human-machine interaction that leads to significantly higher performance by essentially complementing each other. The machine can complement the human and vice versa. Be mindful of collection bias. There's been a lot of cases where, for example, data points are being collected more frequently when there is a known problem. So if you don't account for that in the learning problem, you may bias your training set and hence your model in essentially overestimating those cases of true positive cases. Always start simple. That's the lesson that we have learned. Start simple, get more complex over the course of the project if the simple solution doesn't work, and then get creative. And don't change the sequence. Keep it in that sequence. Always start simple and get creative if necessary. And last but not least, make sure that the first AI solutions that you adopt as a company and as an enterprise are relevant, they're valuable, they bring significant value, and they're extremely successful. Manage the expectations of higher level management, manage the expectations of other teams, and try to maximize the wow factor as you start your journey of bringing AI to the organization. This is especially true for organizations that are early on in the phase of adopting AI solutions. And it's extremely crucial to be mindful of this. And then at the end, I want to highlight the fact that it's important to always love what you do and make a good working environment for yourself, your colleagues, and be able to, in order to be able to achieve big milestones. We are humbled to be recognized by Best Place to Work by Glassdoor, and also among other recognitions, be rewarded as the Disruptor 50 3 years in a row, among other things. With that, I would like to thanks again the organizers, and thank you for listening to us and for your great questions. And we'll be around to answer any questions that might be remaining.
So there are a couple of questions in the Q&A. Do you want to take a look at those? And also a couple in chat.
Sure.
Can you see the Q&A there, or shall I read them to you?
Yeah, I think I am pulling.
I didn't know there was a chat as well. I was just looking at the Q&A. See, answered Bill's question, I think, before. Yeah, so S. Goswami is asking, how did you evaluate accuracy of your diagram digitization network? How many layers are there in the network? And are these object detection or classification networks? So we evaluated the performance of our networks using precision and recall. These are classification networks. So imagine, whatever predictions we get out of that, we just compare with the ground truth using a minimum IOU, so intersection over union, to mark predictions as correct. And using those ground truth labels and the correct predictions based on the IOU, we can calculate precision and recall. So that's how we've been keeping track of the model's performance. In terms of what our architecture looked like, so as you saw, there were 3 convolutional layers, 1 fully connected layer, and then you had 1 softmax layer. So pretty standard LANet architecture. And then we also have a question that says, how does a human compare the machine's interpretation of the diagram with the actual diagram? Okay, yeah, so this can be confusing, right? And what I showed you for the most part is this table view, right? And it may not be very easy to link that table view with the actual diagram. So that's what the UI is for, right? And that's currently in development right now. I think there's another question for you, Mehdi. Maybe says like, what would happen if you applied the methodology to portfolio protection? For example, predicting market crashes.
Very interesting. I go back to the guidelines that I was enumerating in terms of use case selection, right? I think definitely undoubtedly there's a lot of value in being able to predict market crashes, but I think the fact that no one or not many people are being able to do that is a good testimony to the fact that it's probably not a very easy use case or a use case that you want to bet on. Again, I think it goes back to those principles. Is this something that a human can do, can accomplish in a very short period of time? Is this something that we have a lot of training data on? Is this something that I had it in the notes, are the signatures of failure the same? So if we model market crash as a failure of a machine, the economic machine, are the signatures of failures always the same? Which is a big question and a big assumption. I think I'm not an economist, but if you talk to the economists, they will probably tell you that yes, there are some trends, long-term and short-term cycles in the economy and persistent improvement of efficiency. But at the end of the day, each failure or each crash has its own characteristics, and it might not be generalizable to expand that from, if you learn the characteristics of the crash of 2008, you may not be able to predict the one of 2020 or onwards. So yeah, I guess, if that was an easy solution, we would have had quite a few data scientists, billionaires, I guess. So yeah, I wouldn't bet on that.
Are there any other questions? Okay, well, I'd like to thank our speakers tonight. It's a very good talk, so appreciate it very much. I apologize, we have to figure out a better meetup ways that we can share the whole audience applause with you, but we'll work on that in the future.
Thank you, Greg.
Thank you very much and appreciate your talk.
Thank you all, and thank you, Greg and Will and Bill, for organizing. And
I just want to remind all the participants that we do have our natural language processing using PyTorch coming up this coming weekend, a 2-day webinar, 3 hours each day. And so take a look on the SFBACM meetup or the sfbacm.org website to see something about that.
And then a common question many audience members ask is there accessibility to slides? So there's a comment section at the end of the meetup. So if you care to, print to a PDF and add a link to that in the comment section for this particular meetup event. People in the past have appreciated that. So that would be one option for you.
And someone asked about the cost of what I just mentioned, and that was, I believe it's $100. But like I say, take a look on Meetup for us for SFBACM, or on our webpage, sfbacm.org, and there'll be more information there. Thank you. I'm going to end the meeting now. Thank you, everybody, for coming.
Thank you.
Thank you.